Good afternoon. Welcome to the Dev Summit. My name is Ming, Zhao, and this is my colleague, Javier, Delgadillo. And we are both developers for GeoEvent. And today we are going to give 2 talks on how to use the GeoEvent SDK. And I'm going to talk about custom connectors in this session. And then Javier is going to talk about the custom processors in the next session. And we're going to answer questions together after each session. So this is our agenda today. We're going to get a higher level view of the real-time GIS, and we'll show a demo that uses a custom connector, and then dive right into the connectors. Then we'll talk about the transports and adapters. So I'm going to review the product at a higher level. GeoEvent gives ArcGIS server the additional ability to integrate real-time data into ArcGIS infrastructure. It also allows continuous processing and analysis of that data as it is being collected, and then to distribute the results of the analysis to people who need it, when they need it, and where they need it, be that in a live map or email or WebSocket or persistent storage. So GeoEvent receives real-time data using the inputs that are defined by input connectors. So out of the box, we have input connectors that receive or pull data in RSS, text, JSON, or feature JSON formats from sources like TCP, UDP socket, REST endpoints, WebSocket, and ArcGIS server. And we also have the capability to monitor files in folders. And in addition to these connectors that are out of the box, so we also have a list of input connectors that are hosted on the Esri gallery and the partner gallery. Before you develop your own connectors, you should always check these sites and see if someone already developed something that meets your needs. We have mentioned that the inputs are defined by input connectors. So what is an input connector? An input connector is a combination of a transport and an adapter. We will explore that in great detail in this presentation. This slide illustrates how we can create a connector using available transport and adapters. For example, the receive feature JSON from Kafka connector is composed of a Kafka inbound transport and a feature JSON inbound adapter. And the receive GeoJSON on REST endpoint connector is composed of an HTTP inbound transport and a GeoJSON inbound adapter. It's important to note that you can create a new connector that isn't part of the core offering by combining the existing transports and adapters. You can do that on the GeoEvent Manager UI without writing any custom code. So the outbound connectors handle similar flavors of data as the inbound connectors, such as JSON, text over TCP, UDP, REST, and WebSocket. It has a few additional options, such as sending out emails or text messages. And most importantly, the ability to send GeoEvents to a spatial temporal big data store. There are also additional connectors on the Esri and the partner gallery. Similar to inputs, outputs are defined by output connectors. An output connector is again made up of an adapter and a transport. For example, the send an email output connector is composed of a message formatter adapter and an SMTP transport. And the publish feature JSON to Kafka connector is composed of the feature JSON adapter, outbound adapter, and the Kafka outbound transport. When the data is acquired, we can apply real-time analysis to the data, which allows you to filter and process the data. This slide summarizes where you can add your own code to the GeoEvent server. The GeoEvent server comes with an SDK, which allows you to build custom connectors both on the inbound side and on the outbound side, and custom processors, which will be discussed in detail in the next presentation. The SDK provides a number of resources to accomplish these tasks. You can see a snapshot of folders that are delivered in the SDK. It contains an API folder, which is the Java doc that describes the API. And it also contains a set of libraries you can use to compile against when you develop your custom code. The samples folder contains 12 projects for adapters, transports, and processors. They are updated for each release, reflecting changes that are made to SDK if there is any. The developer guide describes the software architecture, how to work with GeoEvents and the GeoEvent definitions, and how to use Eclipse to edit and build components. It also describes in detail that what the takeaways are for each of those samples. Before you start working on your custom components, you should definitely read the developer guide and review all these sample projects. So now I'm going to show you an example of a custom input that received flight data in JSON format from an MQTT server. It then updates the two feature layers that represents the last position of a flight and that's trail. I will use a web map to display the two feature layers and have them refresh every 6 seconds. This is a part of the IoT session demo. And I used a Raspberry Pi and a SDR radio receiver to capture the flight information. It then sends the flight data to the cloud layer, which is an MQTT broker. If you want to know more about the entire project and missed yesterday's IoT session, you're welcome to attend the second offering of that session on Friday. But now our focus is on how to use a custom connector to create a GeoEvent input so that we can receive data from MQTT broker. I have to plug in this slide for background information. We are going to mention MQTT a lot when we demo the input, when we talk about the custom connector and the transport. So what is MQTT? It is a machine-to-machine Internet of Things connectivity protocol. It is extremely lightweight and uses the low bandwidth. So as a result, it is very popular in the IoT world. And it uses a publish-subscribe model. And so it is very easy to use. So let me switch to logging again. All right, so this is the GeoEvent Manager page. And it is showing all the services and the inputs and outputs on that GeoEvent server. We're going to focus on this input here. And I clicked on the input. It should come anytime. No. All right. So this input is built upon this input connector called receive JSON from an MQTT broker. The first part of the properties are related to what the data looks like. And so here we have a radio button here that says whether you want to create a new GeoEvent definition or not. And in this case, we selected no, and we are going to use a GeoEvent definition that we created ahead of time. And then we are also saying that we're going to build geometry, point geometry from the fields. And these fields are long and lat. And the second part of the properties, starting from host, they're related to how we are going to get the data. As we mentioned, this is going to get the data from the MQTT broker, so we have to specify a URL for the MQTT host. And then we need to specify the quality of service level. And as you can see that when I hover my mouse over the question mark, the description of the property is displayed, and it gives you more details than the label. And then we also need to specify a topic here because as I mentioned, the MQTT uses the publish and subscribe model. So we need to subscribe. We need to connect to this MQTT server and subscribe to this topic. So let's take a look at what the data looks like. Oops, not this one. All right. So this is a program called MQTT links. So what it does is it subscribes to the MQTT broker on that topic, and it basically pulls the data in here, and that's all it does. So I'm going to copy the data and put it on a JSON parser, and we can take a look and see what the data looks like. So this is the flight information that we received from a flight sensor. As we can see here, we have 5 different flights that we received, and these are the attributes of the flights. Another thing I want to show is the GeoEvent definition. So if we go to the manager page again and click on the site, and then we click on GeoEvent definitions. Oh, I have to sign in again. So we should see a list of GeoEvent definitions here. And the one that we are going to use here is flight sensor GED. I click on it. All right. So this is the GeoEvent definition. It matches the fields we saw in the JSON file. But it also has a geometry field. So as you remember, in the input properties, we said that we're going to populate this geometry field with 2 fields, long and lat. Okay, another thing I want to show is the services. So if we go back here to the services, GeoEvent service. A GeoEvent service ties together the input and output. And then you can also specify processors in it. So this is the GeoEvent service that is responsible for putting the data on the in the feature layers. It's just slow. Okay, so it looks pretty simple. There are 2 inputs. They're both MQTT JSON input. The difference is that they are subscribing to 2 different topics because I have 2 different flight sensors. And then we pass the GeoEvent to a field mapper. And the function of this field mapper is to add a timestamp to the GeoEvent. And then we pass the GeoEvents to 2 outputs. The first output is update a feature output, and it will update the last position of a flight, any flight. And then I have this add a feature output, and this in here I'm going to update the trail of the airplanes. And we also enabled the auto delete on these outputs so that if an airplane is not updated for a while, will automatically delete it. And then also we can control the length of the trails. Okay, so this is what it looks like. This is the live map. Using one sensor, I have the sensor running in the, set up in my office in Redlands. And these are the airplanes that you can catch. And the web map updates every 6 seconds. It's good that we have some airplanes here. Yesterday, I remember we only had like 3 airplanes by the time I did my demo. And it's interesting to see this airplane. This looks like a helicopter. So that's it for this first demo. So now we're going to take a look at connectors. A connector functionally provides the user the ability to create inputs and outputs. Its purpose is to hide the technical details from the user so that they don't have to look at those details. And it can be very specific, for example, getting the latest earthquake from USGS RSS feed. Or it could be more general, like getting any types of RSS feed. Here's how it looks like architecturally. The user wants to connect the GeoEvent to a number of feeds on the internet, such as National Weather Service, USGS, live traffic. He looks at the list of available inbound connectors. He sees a receive RSS connector, a pull external website for JSON connector, and a receive text from TCP connector. He sees that the National Weather Service provides an RSS feed. So he uses the receive RSS connector to create an input called storm to connect to the National Weather Service and receive data from the RSS feed. And then he looks at the USGS site and sees that they have an RSS feed as well. So he is going to use the same connector to create a second input called earthquakes, which consumes data from USGS RSS feed. So there are two separate inputs using the same underlying logic to connect to consume different data. Now he looks at the live traffic service and sees that they provide content in JSON format over the web page. So he uses the pull external website for JSON connector to create a third input called traffic to receive data from the live traffic service in JSON format. So the user is done with creating the inputs, and the inputs are continuously receiving data from these sources. The connector helps the user through these configurations. It can provide default input. In this case, instead of a generic name, it can provide a more meaningful name, and it can also provide the default value for properties, such as the URL and the frequency properties in this case. It allows you to relabel the properties. So instead of the URL, which may not make a lot of sense to many people, you can rename it to something like RSS address. And you can also move properties into different categories. For example, the polling frequencies property, if the users do not use it very much, then you can put it under the advanced section. Properties in the advanced section do not show up by default. They only show up when the user clicks on the advanced button. And then you can also completely hide a property so that the user will never see it or change it. So in this case, the URL proxy, if you don't want the user to use it, you can put it in the hidden properties category. All these configuration changes can be made either through the UI, the manager UI, or through the code. Diving a little deeper into the connectors again. Functionally, when a user selects connectors, they implicitly select the components inside the GeoEvent server that knows how to receive and send data. We call that component transport. And they're also selecting the component that knows what the data looks like, which we call adapter. With that knowledge, the adapter can convert raw data into GeoEvents and from GeoEvents to raw data. So here is an example of an input. It is created with a connector which specifies a TCP transport and a text adapter. So the input uses these components by starting the transport. And while the transport is running, it will produce a stream of bytes, which the input then passes to the adapter for parsing. The adapter then produces GeoEvents which the input sends out to all the different services that were created to make use of that stream of data. Now let's take a look at the connector that we used to create that input that we just used. All right. So in order to get to the connectors, you'll go to the site on the GeoEvent Manager page. And then click on the connectors here on the left-hand side. And you can see there are a number of connectors here. The connectors that are out of the box, you cannot modify them. So there are icons. There's a view icon here, so you can only look at them. But the ones that you create or the ones that you clone, you can always modify them. So let's find our connector. So when you type MQTT here, it lists all the connector with the MQTT in its label. And this is the one that we used, receive JSON from the MQTT broker. So let's take a look at this connector UI. Okay, so connector UI is the same for edit and create. The only difference is that this button, when you create a connector, it's called create. And when you edit a connector, this button is called save. So connectors have attributes such as name, label, descriptions. And a connector can be either an inbound connector or an outbound connector, or input connector or output connector. When you select input, then this drop-down of adapters will be filled with inbound adapters. So from a list of inbound adapters, we chose a generic JSON adapter. And then similarly, for transports, from the list of inbound transports, we select the MQTT inbound transport. The MQTT inbound transport is a custom transport. It doesn't come with the product. And we're going to talk about how to build this transport and install this transport in a little bit. And also, we have a chance to give the input a default name. So when we create the input from this connector, this will be its default name, but you can always change it later on to something else. So now, once you select the adapter and transport, their properties are listed here under shown properties initially. So that's why I mentioned that the first part of the properties are related to what the data looks like. That's because they are the properties of the generic JSON adapter. And the second part of the properties are the properties of the transport. So what you can do here, as you can see, there are three categories. You can move some of the properties to hidden or advanced properties. And another thing you can do is you can double click on a property and change its label. So if some labels don't make any sense, or you have some custom requirements for the label, you can change it here in the connectors. And another thing you can do is to override its default value. All right. So it's very important, again, to mention that you can, sometimes you need to create a custom connectors even though you don't have a custom component. There are two reasons why you need to do that. There are two reasons why you may need to do that. The first reason is that you may want to have a combination of adapter and the transport that the product doesn't provide. So you can, this is your chance to put up a new connector here. And then another reason is that you may want to modify the labels and default values. Okay, so let's go back to the slides. Let's talk about transports. We have mentioned that we have mentioned the transports and adapters when we described the connectors. So let's take a look at what a transport does. Its basic function is simply to move data in and out of GeoEvent Server. Programmatically, it has 3 basic pieces. Transport definition. This is the class which provides metadata and the properties of the transport. The transport itself that contains the application logic, such as subscribing to an MQTT broker for a message or reading files from a folder. And then transport service. This is the hook into everything else. The GeoEvent server first finds the transport service. It asks for the reference of the definition so it can present properties to the user interface. And when the user clicks on the Save button on the input or output page, GeoEvent Server asks the server service to create an instance of the transport. So you can view the transport service as the gateway to the metadata and the properties and a factory to new instances of the transport. Inbound transport receives the user configured property from the GeoEvent server. It also receives a byte listener, which is a Java interface from the server. And inbound transport is started and stopped by the server. When it's started, it sends data to the server. When it's stopped, it stops sending data. Transport has 5 states in its life cycle. It starts out in the stopped state. When the user starts the input, the transport goes into starting state. It then initializes itself, such as opening socket connections and reading file systems. And after initialized, it goes into started state. Stays there until something happens, such as a user issues stop statement request. It goes into stopping state and closes all the resources, and then the stopped state. So when error occurs, then it goes into an error state. The server can ask the transporter via interface what causes the problem. Outbound transports are just like inbound transports, but in reverse. They get started, but instead of producing bytes, they are sent bytes repeatedly. Their job is to push these bytes to the output destination. The outbound transport also has the ability to take a peek at the GeoEvent it is sending. So this allows the transport to dynamically determine how to send the events. It is particularly useful when you configure send an email, send a text message type of output. So now let's talk about the properties and the transport definitions before we dive into the custom transport code. In order to know what properties are needed by these components, the transport and the adapter define them through their definition class. A definition class contains a list of attributes for the component and a list of property definitions. There are 2 ways to create component definitions. This slide shows an example of an XML-based component definition. It starts with the attributes for the component. This includes name, label, contact, domain version, type, and description. The label and the description are localized. Then there is a list of properties that user can set to define the component behavior. The property definition includes attributes such as name, label, description, property type, default value, and so on. Property labels are what shows up for each property on the manager UI, and the property definitions show up when you click or hover the cursor on the question mark next to the property input box. So both of them are also localized. There are a few other functions that can be achieved through the properties. One of the functions is that we can set the properties to mandatory or optional. And then properties can be dependent on other properties. So in this example, we have a property that says whether we want to compress the data or not. So if the user selects no, then we don't see the compression algorithms property. But if the user selects yes, then we're going to display the compression algorithm property. And some properties can have predefined values. So in this case, we predefined 3 compression algorithms so that the user can choose from this dropdown. rather than entering their own compression algorithms. Here is another way to define properties. This is in the Java class. And this code snippet also shows how we can create a property definition with allowed values in the Java class. So continuing from the previous example, we have a list of allowed values here, and each has a label and a value. And we pass this list of values, allowed values, to the property definition when we create the new properties. So now we're going to dive into the actual code that creates the MQTT inbound transport. All right, so this is the Eclipse IDE. I hope you can see this project structure here, because I don't know how to increase the fonts, but the text editor should be easy to see. So when you create a component project, well, basically we use Maven, so you can create the project as a Maven structure. And if you download the MQTT project from GitHub, you'll have two folders. One folder is a parent folder, and within the folder, you have the component folder. So we can see we have the MQTT inbound transport here, and then we have MQTT inbound transport service, and then we have MQTT outbound transport and outbound transport service. So let's take a look at the service first. So here, a transport service extends the transport service base. And then when the transport service constructor is called, we get a reference of the, oh, sorry, I need to make it full screen. We get a reference of the transport definition. So in this case, the transport definition is an XML. So we have a helper method that converts the XML to the definition class. So now let's take a look at this inbound transport definition, XML. So as we mentioned earlier, the transport definition contains the attributes for the component itself, such as name, label, contact, version, domain type, and description. And then we have a list of transport property definitions. Here we have a number of properties. We have the host property, quality of service property, and this property, you can see it has allowed values. And then we also have the topic property and username and password. Now let's take a look at the transport. When the transport, it extends the inbound transport base, and also it implements runnable, so you can use it as a thread. And another thing I want to mention is that this transport uses a library called PAHO. It's a library that helps you to work with the MQTT protocol. Another thing I want to show is that since we use Maven, I'm not sure if you're familiar with Maven, we need to define the dependency in the Maven POM XML. So this is basically the library, the PAHO library. So let's go back to the transport. So when the transport starts, it starts itself as a thread. And then when the thread starts, of course, it calls the run method. And here, it in turn calls the receive data. So the first thing it does is it calls apply properties. So this method basically reads all the user-defined properties. You can see it's reading the host here, and then topic, and then username and password, and QoS. Then it sets the running state to started. Oh, sorry. And then we create a new MQTT client. And this is all part of the PAHO library that we're using. And then because MQTT uses publish and subscribe, we basically here we have to set a callback method. So when the message arrives, then this method is called. It gives us the topic and the message. The message body is an array of bytes. So when we receive the message, we send the message body to the receive method. And in the receive method, we convert the array of bytes to a byte buffer, and then we send it to the byte listener. So after it sets the callback method, it basically is ready to connect and subscribe. But here we have some users helped us. They contributed to this repo on the GitHub. They added the option to passing a username and a password and the SSL properties. So this is basically how you would use the username and password. And then eventually you would connect the MQTT client and start subscribing to that topic. And then another thing is when it stops, when the stop method is called, it first disconnects the client and then closes the client, and then it sets the running state to stopped. So as you can see, we saw examples of the localization in the XML and in the XML code. And here we also, when we log a message, we also passing the key to the localized message. So where would the GeoEvent find the localized message, the translation? So basically, there's a property file that has the key and the value of the message that you want to localize. And it all depends on the group ID of this project and the artifact ID of this project. So let's go back here. Let's look at the Maven again. So the group ID for this component is com.esri.geoevent.transport. So under resources, we have a folder called com, and then under that we have Esri, under that we have GeoEvent, and under that we have transport. And then the name of the properties file should match the artifact ID. So in here, in this example, the artifact ID is MQTT-transport. And so we have an MQTT-transport.properties, and then we also have an MQTT-transport_locale.properties. So when the UI detects that the locale is EN-US, then it will be using this property. And here we're seeing the keys and the values. And if the locale detects that it's a Chinese locale, then it will be looking for a Chinese translation property. Then you will be seeing the Chinese here in Unicode instead of English. But if it couldn't find it, then it will be using the default properties file, which is this one that doesn't have any locale. Another thing I want to mention is that since this is a OSGI component, we need to set up some sort of OSGI configurations. And Javier is going to talk more about this configuration. And I mention it here because I want you to know that this configuration is for all components, like transport adapters and processors. Okay, so now we have the transport, and now let's try to build this project. Okay, so if you download the project from GitHub, as I mentioned, you'll have a parent folder, and you have a subfolder, which is a component. I would recommend if you are building your own component, you follow this structure. Because sometimes you may not have, in addition to transport, you may also have adapters. So you notice that in the parent folder, we also have a POM file, so we can build the project right here. All right, so the project is built, and now let's go to the component folder. After we build the project, there is a target folder. So if we go to the target folder, we see the jar file that we built. And as I mentioned, that the core product doesn't have the MQTT transport, so we need to install this transport on GeoEvent server. So we need to first copy this jar file to the machine where you run the GeoEvent server. And then from the GeoEvent server, you'll go to site, and components. And then you can see there are 3 types of components here. By default, it sets transports first, and then you click on Add Local Transport. And you choose the file from the local disk, not from a disk from over the network. Okay, once you install the transport, you will see it in the list of transport here, MQTT inbound transport. All right, so let's go back to the slides and finish up. Let's talk about the adapters. So similar to a transport, an adapter is packaged as a jar file with several classes in it. The adapter has definition, just like transport does, which provides metadata of the component, things like name, description, and the properties. It also contains the functional code, which is the adapter in this case. The adapter implements the application logic. And there is the service, the adapter service. Just like the transport service, it consumes the definitions and serves as a factory for instances of the adapter. The behavior is slightly different. It has properties like transport and has a listener which can send results to. But instead of listening for bytes, the listener listens for GeoEvents because inbound adapter converts bytes to GeoEvents. And another significant difference is that the adapter is data-driven. It doesn't get started or stopped by the server. But whenever data is sent to the adapter uses its special knowledge about the data to convert the data to GeoEvents. So in this example, we wanted to create an adapter that can convert fixed format binary data into a GeoEvent. The incoming binary data contains an integer which we want to use as the track ID, and it also contains 2 doubles for longitude and latitude. So we want to convert this data to a simple GeoEvent which contains a track ID and a geometry field. So the code here is a Java class that defines the adapter definition and the properties. So first, in the constructor of this definition class, it creates a GeoEvent definition. So as we know, each GeoEvent must have a GeoEvent definition. The GeoEvent definition defines the fields, their types, and the cardinalities. Because the adapter has the knowledge of what the data looks like, it is naturally the place where we would create the GeoEvent definition, if you don't already have one. So in addition to create a GeoEvent definition, the adapter definition class also defines the same attributes about the adapter as we saw in the transport definition XML, such as name, labels, and description, domain, contact. Here we see again the pattern used to bring localized string into the XML or Java class when you are not using a log method. So the main method that we need to be concerned about in an adapter is the adapt method. As we mentioned earlier, the data we want this adapter to parse is a piece of binary data which contains an integer and the two doubles. The integer will be used as the track ID, and the two doubles are longitude and latitude. So when the adapt method is called, a byte buffer is passed to the adapter. The adapter uses its knowledge of the data to get the track ID and the X and Y field from the byte buffer. It also creates a map geometry object out of the X and Y field. Then it creates a new GeoEvent using the GeoEvent definition that was defined in the previous in the property definition class. It sets each field of the GeoEvent and returns the GeoEvent. A real-life adapter may be much more complicated than this. You may be using some additional libraries to help you to parse the raw data. Or you may have some additional algorithms to set here to parse the data. But the workflow is very similar. On the inbound side, the adapter receives raw data in byte buffer. It returns GeoEvents to event processing framework so that the GeoEvent can be made available to appropriate services. On the outbound side, instead of the adapt method, there is a receive method which receives a GeoEvent each time. The outbound adapter will convert the GeoEvent to raw data and turn the bytes to transport by calling the receive method of the base class. So in this presentation, we have examined connectors. They can be considered as recipes for inputs and outputs. And we have also looked at the transports, adapters, and properties. We talked about the GeoEvent SDK, which is the building block of all custom transports, adapters, and processors. The samples and the GeoEvent developer guide provides a rich resource of knowledge if you want to build your own transports, adapters, and processors. And here are some additional resources that can help you with to get started. You can access the product homepage using the link above, and you can find all sorts of useful information regarding the GeoEvent server on this page, such as install guide, system requirements, tutorials, galleries, and links to GitHub repos. And before you develop your own components, please check out the galleries and the GitHub repos and see if you can make use of anything there. And if you have further questions, you can go to the GeoEvent forum, which is accessible via the second link. The forum is monitored by our team member. Here's a list of the sessions that will take place later. If you are interested in the flight data collection project and missed the first IoT session, then you're welcome to attend the second offering of that session on Friday. And also, please fill out the surveys. Your feedbacks are extremely valuable to us. Thank you again for sitting through this presentation, and I hope you really enjoy it. And I hope it meets your expectation. And we have these two links up there again, and also with our emails, and hope you enjoy the rest of the conference. Thank you. So if you have any questions, can either, yes?
What's an effective method for writing tests of the connectors, adapters that you're creating, especially integration tests?
Integration test? Let's see. You want to answer? Yeah. Yeah.
Well, in practice, what we tend to do is we write unit tests for the transport and the adapter sort of separately. We don't have a framework for sort of doing the whole integration of while GeoEvent is running, simulating the whole environment. But we tend to unit test each component separately. But if you wanted to, I guess you could write your own framework that sort of try to do some multi-threading stuff to have concurrent events going through your adapter and your transport. But we tend to do that as part of our QA testing. and we tend to just unit test the individual components separately.
Okay, thanks.
Welcome. Yes.
About the parsing part of the adapter, would it be possible to parse natural strings,
Natural strings.
natural language strings coming? I'm thinking about WhatsApp chat. You can export. It's just a text file, many rows each message, and you might have some keywords you want to detect, or maybe a special character like @ followed by an address you could use for geocoding.
Right.
Would it be possible to do something like that?
Well, the thing is that adapter receives any sort of data in byte buffer, right? We mentioned, and the output is a GeoEvent. And as long as you can convert whatever text that you receive and put it in a GeoEvent, it's okay. I think you can write some algorithm to parse the free text and extract the data out of it. I think that's okay. The only thing you need to be aware of is, since it's free text, you have to pass all these text all in one shot. The reason I said that is because if you are reading from a file, it may send multiple, it may chop the file up and send multiple requests to the adapter, and then the adapter will have a problem not knowing when the end of the file is. But if you are sending the entire text through TCP or HTTP, there shouldn't be any problem. You just will be responsible for your own algorithm to get the data out of the free text. Yes?
So presuming we have the case where we have, let's say, 20,000 GPS devices feeding data in, and they don't feed just GPS data, they feed more stuff than that. So it may take a bit of processing to get the data through the filter. How can we find some more details about the limitations? How many messages per second can we process? Presuming this listens on a UDP socket, so at any given moment you may get like several thousand messages per second. How do we scale all of that up and how do we find out about limits?
Well, when you're talking about 20,000 GPS units, you might need to talk to Adam about the next generation GeoEvent. I don't know. He will have
I picked
roadmap.
GPS just as an example. In my case,
Right.
it will not be GPS data. It is specific other real-time data.
Yeah, as well, so what we've done in the past, I'm not sure if Adam is doing it in this year's best practices talk, is we sort of benchmark. This is a server on this hardware, whatever we have. We take a CSV input over TCP, pipe it straight to a TCP text out. So it's just parsing CSV, sending it CSV out again. So that's sort of minimal overhead. Over there, we were on our developer grade laptops. We were doing about 4,000 events per second. And so then the test kept going, and then he said, okay, now we're going to do some sort of geometry operations. We're going to do some geofencing with very simple geometries and then more complicated geometries, and sort of he published the numbers of what the sort of degradation was on the same hardware, given those tests. But I don't remember seeing that in this year's slides.
Yeah.
If you go find Adam at the booth this week, I'm sure he'll tell you where to get the latest numbers. But that was our base, sort of 4,000 events per second.
That's like, do they get processed one at a time, serialized, or can they be processed in parallel?
It's a parallel. The services spawn threads, lots of threads, so you're not guaranteed to process them in the order that they're received. So some people come by and they want that guarantee, and we say we can't. Because to do that, we would severely impact performance.
Okay.
Right.
Thank you.
It also depends on your output. If you use, for example, if you use stream service output, the throughput, the performance is a little better. But if you're using like a feature service, then there may be a bottleneck somewhere in the system. Yeah.
For a stream service, if your incoming data more particular, GPS unit, whatever, if its location hasn't changed, do you know if there's a good way to filter that out from being updated again?
Location hasn't changed, but you are still receiving the data.
Track idle, maybe?
Track idle, it gives you an alert if the location hasn't changed for a certain amount of time. It's a process. It's a custom processor.
What was that?
It's called a track idle processor.
Track idle?
Yeah. From the product, we have something called track gap processor. It comes with the product. So if you haven't received the event on a certain track ID for a certain amount of time, then it will send an alert. But track idle, it tracks events that you received but didn't move for a certain amount of time. But it doesn't remove the feature, or doesn't. Yeah, it still shows up.
Are you trying to remove it from the viewer or from somewhere else?
Not necessarily. Just stop from continually sending this same locations.
You can maybe put an alert.
With something that hasn't.
Right. So instead of removing it, you maybe you can put an alert on it and just say that it hasn't moved. Yeah.
You might be able to write a custom processor to do that, because we have there are processors that keep state, like the track idle detector is one. So it's just a matter of sort of remembering the last known position. If it's the same, just sort of drop it.
Right.
Yeah, I was thinking maybe like a processor with the in-memory store that track.
Right.
Yeah, because the track idle detector processor does something very similar to that. It's but the opposite of what you want.
I have some follow-up question on how can we tie user security permissions through the processor. So, for example, some users will have permissions to see some events, and other users will not. For other users who want some of the data stream. Would that be part of the GeoEvent, or do we do that on the ArcGIS server?
You do that on the ArcGIS server. You give GeoEvent, based on the output you use, you give that output the appropriate permissions to update whatever it needs to update. And then your viewer, whatever your viewer is querying, that guy has to sort of put the access controls so that the user can't get to the records that you're trying to hide. Any more questions? All right. Thanks for coming.
Thank you.